Hello, everyone. This is going to be the lecture for section 6.1 and 6.2 for our Math 210S portion of our course, graphs of trigonometric functions. Okay, so in chapter 5 for pre-calc, right, we defined angles, we played around with the angles, we picked up what sine and cosine are, and as an extra, we picked up what tangent is, right? And we saw how all of that worked with right triangles, and we got to play around with some expressions, right? So we know what sine and cosine, and to an extent a little bit, right, what tangent is, right? And what it's supposed to do for us, right? Uh, what we're going to work on now is basically all of the graphs for all 6 of the trigonometric functions, okay? We'll do some examples. This is going to take a long time. I think this section is like a good 9-10 pages, okay? So a lot of our time is going to be concentrated into grabbing the pictures of each one of the sine, cosine, all the trig functions, right? And trying to make sense of them, at least trying to sort of make sure that we can make sense of certain portions of sine, cosine, tangent functions if we see them in the wild, right? Okay. First thing, though, is I got to show you what they look like, okay? So the first thing I want to do is I want to go ahead and graph sine of x, and I'm going to do it in a particular way, okay? I'm going to use the unit circle, okay? So hopefully you all have seen this little yellow pamphlet thingy that has the unit circle on it, right? So we're going to go off of that exactly, right? Hopefully you guys have it in front of you, right? Okay. So if you look at the unit circle, the first thing I have to recall for everybody, right, is this, that if we're looking at the cosine function, right, that is looking at the x values, right? And the sine values, those are the y values, right, on our unit circle, okay? So that's actually all we need, okay? So now what I'm going to do is this. I'm going to go through, a handful of angles. Those are going to be my x values. And then we're going to see what the sine of x of those angles are going to be, okay? And then we'll throw them on an axis, right? So to start, right, if we take a look at the angle 0, right, we see that the y portion of that is 0, okay? If we keep on going up now, we're going to go in the positive direction, right? If we go to pi over 6, that is going to be 1/2, okay? If we go to pi over 4, that is going to be square root of 2 over 2, which is about 1.7 and change, right? Pi over 3 is going to be square root of 3 over 2, and then pi over 2 is going to be 1. Okay, 2 pi over 6, hopefully you guys see this. This reduces to 2 pi, or sorry, am I right? Yeah, 2 pi over 3. Aha. 2 pi over 3. And if you take a look at that, right, that's going to be square root of 3 over 2. 3 pi over 4, that is going to be square root of 2 over 2. 5 pi over 6, 1/2, and that pi, 0. Okay, we're going to jump a little bit. Let's go to 3 pi over 2, which is the angle that points straight down, right? That's going to be -1. And then the y portion of our point at 2 pi, that is going to be 0. Okay? All right, so now what I want to do is I want to slap these onto an xy plane, right? Okay, so I'm going to do it in a nice blue color here, okay? I'm going to go ahead and go through the angles, okay? So at 0, it's 0. Bam. Okay. At pi over 6, it's 1/2. Okay. At pi over 3, that's going to be, where am I? Root 3 over 2, so just below right there. At pi over 2, it's 1. Okay. And then it starts to drop, doesn't it? So root 3 over 2, square root of 2 over 2. Whoops. Oh, sorry. 5 pi over 6 is 1/2. And then at pi, it's 0, right? Let me scroll down a little bit. At negative root 3 over 2, at negative 3 pi over 2, it's negative 1. And then at 2 pi, it comes back up here. Okay? Let's connect the dots like we really did in kindergarten, right? Bam. Bam. I skipped a couple values, but that's all right. There we go. Hopefully you guys see that shape, right? This is sine. This is the sine graph, okay? I want to point something out now that we're all here, right? You see the table that I wrote down, right? And you see the values. There's really 5 critical values that we need to plug. It's this one, right? This one, this one, this one, and this one. Those are really the 5, and they match up to this point right here, this point, this point, this point, and this point. If you have those 5 points, you get the sine squiggle, right? Does that make sense? All right. Awesome. Okay, let's keep going. All right, let's move along. The next one that I want to do is cosine. The next one that I'm going to do is cosine, okay? So now, we know that cosine is the x portion, okay? So let's go through our unit circle and let's graph those, right? So at 0 degrees, it is 1. At pi over 6, we're looking at root 3 over 2. At pi over 4, that is root 2 over 2. At pi over 3, that is 1/2. At pi over 2, keep in mind, we're looking at the x value now, right, of our coordinate because we're looking at cosine. So then this is going to be 0. And then it starts going negative. You guys see that? So it's going to be negative 1/2, negative root 2 over 2, negative root 3 over 2, and negative 1, right? And then I'm going to speed up the process again. I'm just going to do the last 2 angles. The one that's pointing straight down, that's going to be 0. And then 2 pi, it's going to become 1 again, right? Okay. I'm going to do the same thing. I am going to slap down some of these points on the xy axis that I have here, right? So there's 1 point. Square root of 3 over 2 is about right there. Root 2 over 2 is a little lower, right? At pi over 3, where is my pi over 3? Oh, I went too far there. Pi over 3, it's going to be at 1/2, right? And then at pi over 2, it's going to be 0. There we go. Got ahead of myself a little bit. And then it's going to keep going, right? So it's going to go, let me actually scroll down a little bit. So there we go. At 3 pi over 2, it's going to be negative 1/2. And then it's going to go root 3 over 2. And then at pi, it's going to be negative 1, right? And then here's where I sort of expedited the process a little bit. At 3 pi over 2, back at 0. And at 2 pi, back at 1, okay? So again, connect the dots like we did in kindergarten, right? Bam. And bam, right? And then we're just going to keep going. Boom. Boom. There we go. Okay. This right here is the cosine squiggle. Okay. And again, just like we did from before, right? Thankfully, it's actually the same handful of angles that we need to really concentrate on. It's these 5, right? It's the one at 0, pi over 2, pi, 3 pi over 2, and 2 pi. So for both sine and cosine, they are the angles, the north, south, east, west angles, basically, right? The up, down, left, right angles. So long as you know where those angles are, right? What those values are, you're golden, right? You guys see, hopefully, there we go. Okay. This right here will tell you everything you need to know for sine and cosine. Okay. All right. A couple things about sine and cosine. Okay. They are what we call uh, periodic functions. So periodic means that they repeat. They have something that repeats. In this case, the whole function repeats after a little while, right? The periods for both of these is a distance 2 pi. So if you go back up to the functions themselves, right, you get to see that after I do 2 pi, right, if I go a distance 2 pi, that function just repeats and repeats and repeats and repeats. Okay, all right, we're getting somewhere. Okay, so periodic means it repeats. Okay, the domain of each one of these functions, so remember, right, the domain that we're talking about is that x value, right? And if you remember, those x values were angles. We can go as many spins around the unit circle as we want, either positive or negative. We'll get an x or a y coordinate, correct? Okay, and the range is going to be -1 to 1. So basically saying that the x values can be anything we want it to be, right? And the y values are going to be somewhere between -1 and 1. Okay? Uh, a sine graph, we say that it is odd. Okay? So that means that this is going to be symmetric about the origin. Okay? What this basically says, right, if you recall, is that if we can grab our sine graph and flip it along the x and the y axis, and we get the same shape. Okay, as opposed to cosine. Cosine is an even function, right? So that's only symmetric about the y-axis. What we're basically saying there is that we can grab our function and flip it across the y-axis, we get the same graph, right? So if you take a look at it, right, we get to flip this way, right, and this way, and we get the same graph. Cosine, we can only do one direction. We can go whoosh. That's it. Okay? All right. Let's keep moving along here. These graphs have a specific name behind them. We call them, in the sciencey world, right, we call them sinusoidal. Basically saying that they're going to be squiggles of some sort, okay? Their general form is going to look like one of these two, either this one for sine or this one for cosine, okay? Now, you guys see how I have them sort of separated away there. There's an A, a B, a C, and a D for everything, right? So what I'm going to do here is I'm going to cover each portion separately, okay? The first thing that we're going to take a look at is the amplitude of a sine and cosine wave, right? And that is exactly what you think it is. It is that it's going to be that A that's up front, okay? Okay. The next thing that we're going to look at is the period. So sometimes we can have a period that is something else that's not 2 pi, right? I like to say vanilla sine and cosine have a period of 2 pi, right? But they don't have to. We can squish it or we can stretch it out, okay? And the way that we find that period is by an equation t, which is equal to 2 pi divided by my value b. And it is exactly this b that's inside the parentheses. Okay? All right, we're getting somewhere. We're getting somewhere. Okay, next thing, a phase shift. Okay, so sometimes a function, a sinusoidal function, a sine or a cosine function, can present, it'll look like one, but it may be shifted left or right a specific amount. Okay, and that amount is given by C over B. Exactly the C over B that you see from right here, right? Okay. Now, this one works a little weird, right? If you do C divided by B, right, and it's equal to negative, right, then that meant you moved it to the right. Okay. If you did C divided by B, and that is a positive value, then you move it to the left. Okay. This is weird. I know it is. It should feel weird. because you're moving it in the opposite direction of the number. Turns out that's how it works out. At least it's simple, right? Okay. Last thing I got to cover, vertical shift. Okay. And that is going to be equal to that D value. And the midline is going to be that Y equal D value. It's basically this D value right here at the tail end. Okay. This is basically telling us that we're going to grab our graph and move it either up or down. Okay. So we've got all the bits and pieces. So let me put them all on a graph, right? What tends to happen, right? I can grab this thing, move it left or move it right, right? According to the C over B, this is my phase shift, right? There is a distance up and down, okay? And I'm going to draw in the distance first before I explain the rest of it here, okay? Either up or down, okay? From my midline. From my midline. So hopefully you guys see this. Here's my midline. You see how it sort of slices my graph in half, right? This right here is my y is equal to d. Okay, that is my midline. That's what my vertical shift, what I need to move it up, down, left, right to. Okay, well, up, down for sure. Okay, from that midline, I have my amplitude. Got it? Okay, and the amplitude is the distance from the very middle, from my midline to either the tippy top or the absolute bottom. Okay, and then there's one last thing to explain here, and it's this, that from here, right, to here, okay, you guys hopefully see that this is one period right here, right? That is one period from there all the way out to right there, right? That is one squiggle of sine, okay? That is determined by the t value, which is 2 pi divided by my b value, whatever shows up in that function, okay? There you are. That's all the parts for sine and cosine, okay? I want to do an example, okay? So hopefully you guys see this. Yeah, okay. Let me scroll it down a little bit more. So there we go. Okay. I know this is sort of going backwards, but I mean, like I said, right? A lot for the class, we're gonna have Desmos. We're gonna be able to grab these functions and throw them into Desmos and get a representation for them pretty easy, right? However, I do want people to be able to, if I show you a function, right, then you should be able to pick out the small little portions, the bits and pieces of everything, okay, so that you should have sort of like a mental image of what one of these functions should look like, right? Or at the very least, how to grab one of these sine, cosine functions and transform them appropriately so that you can, like I said, have some sort of a picture of what they're going to look like, okay? All right, so for this one, we're going to find these four things, right? Midline, amplitude, period, phase shift of this function right here. Okay? Okay. So I'm going to write it right up above, right? This is going to be a plus or minus an A sine bx plus c plus d. All right? All right, let's start with the easy hanging fruit, right? Midline. Bam. We're looking at this thing, right? The midline, hopefully you guys see it, it's going to be y is equal to positive 1, right? And that is this thing. That is that thing at the tail. Okay? Next one, amplitude. Okay? That amplitude is going to be A is equal to 3. Hopefully you guys see it. Bam. That's that 3 up front, okay? So this is telling me, right, just these two pieces of information are telling me that my function is going to get moved up to y equal 1, right? And from y equal 1, it's going to go up and down that much, okay? All right, we're getting there. Let me do phase shift, Okay. Hopefully you guys see that there is, if we match up, you guys see that there's a B, there's the B, but there is no C, right? You guys see that there is no C there. That means our C is 0. So my C divided by B, C divided by B is going to be 0 divided by 2, 0. So this thing we don't move left to right at all. Okay. Our original picture of sine for this example, right? Our original picture for sine of this example starts at 0, 0. We don't move it left to right. Okay? One last thing, my period. Okay? My period is given by this equation, right? T is equal to 2 pi divided by b. So we know what b is from our equation. Bam, it's right there. Right? In our case, it's this 2. 2 pi divided by 2. You guys see the 2's cancel. So my period is pi. This is telling me that my function, right, the original vanilla version of sine and cosine, their period are 2 pi, right? By computing this, I got that this period should be pi. So I should get one repeating cycle, right, of sine and cosine within pi. All right. So if you take a look at the function or the graph that's on the left here, right? Kind of cheating a little bit. We already have it done, right? So now let's tie in all the stuff. Okay, so if you take a look, use my midline, right? That is that red line that goes straight across, okay? And that's at 1. Whoa, okay. I don't know why I did that, but okay. We'll work with it. Okay, next up, my amplitude. You guys see how it goes up and down by that fixed amount, that set amount, right? This distance right here and this distance right here, they're both 3, okay? It starts at 1 and it goes up to 4, right? That is a distance of 3. It starts at 1 and drops to -2. That is a distance of 3, okay? Phase shift. Hopefully you guys see this, right? The graph starts right here, right? And it squiggles. It does one good old regular sine squiggle without moving. I didn't have to pick up my graph and move it left to right at all. Got it? Okay. And then the last bit, hopefully you guys see this, right? The period. It's supposed to be pi. That one squiggle that I drew, right? The original sine graph will do this. It'll go up and then hit this one. Let me get rid of some colors. There we go. It'll go up, hit this one, and then come back down and go back up, right? Yeah. This one's vanilla sine. Okay. The period for vanilla sine, regular, good old regular sine, is 2 pi, right? This one has pi. The period for this one is pi. So it starts here, but then has to end here at pi. So you guys see that's pi, right? And that's exactly what happens. Here's one squiggle of this function right here. Okay, so hopefully you guys see that all of these things, all of them, all 4 things, right, sort of show up visually in the graph of this function itself. Okay, and that's really what I want everybody to pick up on. That, yes, we can grab all of this and throw it into Desmos. It'll give us a picture, right? Okay, but what I kind of want to do, what I kind of want to show you guys is this, that, you know, pretend, right, we don't have none of this, right? Pretend we don't have that. How would we graph our function? We should be able to pick out certain things from this function and automatically assume that they're going to appear on our graph somehow, right? And this is it. This is what's happening. Okay? All right. Oh, my goodness. Let's keep going, huh? Okay. I've got some quick checks for you to practice on. Okay, these might take a little while, so we'll go through all of these. Okay, so I just did sine and cosine. Okay, the next one that's going to show up now is tangent. Okay, so if you recall, tangent is equal to, right, sine of x divided by cosine of x. And we remember this, we remember sine to be the y portion, right, divided by the x portion. Right? Okay? So we're going to go through the unit circle again, and we're going to look at y divided by x's. Okay? And I've got a couple of angles here ready to go. Okay? These are the ones that I'm really going to be concerned with. And then I'm going to show you guys the ones that you should be using to draw them if you need to. Okay? Okay, here we go. So if you do negative pi over 2, that's the angle that is pointing straight down, right? We need to do minus 1 over, and let me move this over a little bit. Come on, there we go. Minus 1 divided by 0. Hopefully this is ticking you guys off to something, right? This right here, right, does not exist, is undefined, right? Okay, we'll come back to that in a second. But for now, right, that is definitely something that should tick you off. It's an undefined, right? Okay, let's keep going. Negative pi over 4, that is the same thing as the angle that's at 315 degrees, right? So that's going to be negative square root of 2 over 2 on top, divided by the square root of 2 over 2 on the bottom, right? And if you take a look at this, this is going to be negative 1. All right. At 0, that is going to be 0 divided by 1. 0. Great. Thank goodness, right? Okay. Next one, pi over 4. So we're going to look at the 45-degree angle, right? And we're going to look at those two values. So it's going to be root 2 over 2 on top, divided by root 2 over 2 on the bottom. Okay? That is equal to 1. And I'm going to do it again. I'm going to do pi over 2, right? That's going to be 1 divided by 0. Again, this should tick you off, right? This does not exist as well. Okay? I'm going to highlight those two does not exist. And there's a reason why I'm going to highlight them, and I wrote them in red. Okay? If you take a look at what we have below, here's our picture for tangent. Here's our picture for tangent. Here it is right here. Bam. Okay? Okay. I want to really concentrate on these. On this. And this. Okay? All right. If you take a look, right, at pi over 2, or sorry, pi over 4, that's going to be a negative 1. That's going to be that point right there. 0, positive 1. So each one of these, if you take a look, right, this is going to be negative pi over 4, and this is going to be positive pi over 4. Okay? Again, right, the three angles that we really need, right, are this one, and this one. I think everybody can see that outside of that, we know what direction the squiggle goes, right? We just have to look at the good old regular vanilla one, right? And then we got the rest, okay? Now, what I want to point out is this, right? Is you see those pink highlights, right? Those are actually asymptotes. Why? Why are they there, right? So if you remember the asymptotes back from chapter 3, maybe what, second, third week of class, right? Those asymptotes happen when the denominator of a function is equal to 0, right? So if you recall, right, tangent is equal to sine of x divided by cosine of x, right? Asymptotes happen, right, when let me do this. Asymptotes happen when cosine of x equal to 0. Okay, essentially saying the bottom, right? Bottom. Let me put that over here. Bottom is equal to 0. Whenever the bottom is equal to 0, you're going to have an asymptote, right? So that means cosine of x is equal to 0, right? Okay, if you recall, the cosine of anything on the unit circle is the x value, right? The cosine is the x values. Where are the x values equal to 0? Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, dot, 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 dot. And it keeps going because we can take as many laps around the unit circle as we want, right? And they keep going in the backward direction, right? Minus pi over 2, minus 3 pi over 2, dot, 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 dot. So these are our asymptotes, right? These right here are our asymptotes. Okay, so we have the general theory of how to draw one of these tangent functions, right? Is this what we really do every time? Hell no. Heck no. Okay, there's a nice little, let me actually put these two together. There we go. There's a nice little table that I have here. It's from our textbook, from the pre-calculus textbook that I spelled out at the beginning of the semester, right? Okay. In particular, I want everybody's attention to go to this row right here. That one. Okay. What we really need, is where those asymptotes are, right? So long as we know where those asymptotes are, we draw a squiggle in between them and we'll be all right. Does that make sense? Okay. So what we really need is those asymptotes. Okay. And that's exactly how I'm going to figure out how to sketch 2 periods of this thing right here. Okay. So here we go. And actually, let me bring this back up. I want to bring this up real quick. This does have a formula that we have to sort of evaluate, right? K has to be an odd integer, so an odd whole number for tangent. Okay. This is something that's going to get confused with the same box but cotangent. Okay. Just keep it straight when you get to your flashcard, right? If you're going to put this on a flashcard for a test, make sure you put down that K for tangent. That K value's got to be an odd integer. And that's exactly what we're going to have to use when we start graphing them, or when we start figuring out the asymptotes for tangent. Okay? Okay, so here we go. Okay, the formula for the asymptotes, right? I'm going to rewrite it really quick. C over B plus pi over 2 times the absolute value of B. We tend to drop the absolute value times a value K. Okay, K's got to be odd. K has to be odd. So what I'm going to do is I'm going to choose some values. I'm going to start with K equal 1. 1 is the very first odd value, right? So if you take a look at this, right, this is already a Y is equal to A times some tangent, right, of bx plus c plus d. Okay, we're getting there. So we know what we have here. That is a b value, right? Okay. There is no c value, so this is going to be x is equal to 0 over pi over 2 plus pi over, whoa, let me write this a little nicer, huh? Pi over 2 times b pi over 2 times 1, since my k was 1, right? Okay. 0 divided by anything, that's going to be 0. Plus, this all reduces to pi over pi times 1, 1. Okay. I want to take a look at this right here. So when k was 1, my asymptote's at 1. Okay, let's keep going. Let's do the next odd value. K is equal to 3. Okay, x is equal to 0 over pi over 2 on the bottom plus pi divided by 2. Pi over 2 times 3. This is still going to be 0. Plus pi over pi times 3. 3. So when k is equal to 3, my asymptote's equal to 3. Okay? So hopefully you guys see what's going on here. Okay? When k is 1, right, my asymptote's at 1. When k is 3, my asymptote's at 3. Okay? What I like to say when I teach this in a pre-calc, right, is you tend to use only maybe the first two, maybe a third one, and what you start to see is a pattern. A pattern starts to show up. So hopefully you guys see this already, right? We did k equal 1, k equal 3. The next odd value, k equal 5, okay? Take a second. What do you think it's going to be? Good. Let's figure it out. X is equal to 0 divided by pi over 2. Also notice that the math is just repeating, right? The only thing that's changing really is this thing, right? 5 at the end, the k value, right? Equal 0. Let me actually make that a big 0. 0 plus pi over 5, pi over pi times 5 equal 5. Bam. Okay? I'm pretty sure your guess was right. I'm pretty sure your guess was right. Okay? So then now let's go ahead and let's keep on going, right? Let's, k equal 7. Hopefully you know what that one's going to be, right? So x is going to be equal to 7. K equal 9. X equal 9. These are going to be the asymptotes that come out if you compute those values, right? Okay, so I'm going to summarize here. Asymptotes. Add x equal, and I'm going to put it like this. It's going to be 1, 3, 5, 7, 9, dot, 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 right? And we can go backwards, right? -1, -3, comma, dot, 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 dot. Okay, there we are. Let's graph it. Okay. So to graph this, right, I'm going to go ahead and I'm going to make this. Uh-oh. You guys have no idea how hard it is to draw on this thing. There we go. I'm going to make that my y-axis. This one's going to be my x-axis, right? I'm going to try to draw this thing. Okay, I'm going to try to use the same colors that were used when I explained it the first time, like when we defined it, right? So remember, what we had was that at every, was that at 1, at 3, at 5, at 7, at 9, and everything in the negative direction, the same order, right? That's where the asymptotes were going to be, right? So there's going to be 1 right here. I'm going to do this. This right here is going to be 1, 2, 3, 4, 5, This is going to be 6. We don't really need it, right? And then we're going to go backwards, right? So -1, -3, -5. Okay? Let's stick in those asymptotes. There's one of them. There's another one. We know that there's one at 5. Whoa, whoa, whoa. Kind of hard to draw. There we go. And then at -1, there's going to be one. At -3, there's going to be one. You guys see why we had to find them first, right? We wouldn't know where to put the tick marks on our graph if we didn't find them first, right? Okay, and now we get to draw the actual function, right? And we know that tangent, good old vanilla tangent, goes like this. It goes through the middle and then whoosh upward, right? Bam, done. The next one. We know that between any two asymptotes, we've got the tangent squiggle. Bam. Okay, and just for kicks and giggles, let's just go ahead and finish this out, right? Here's another one. So I did more than 2 periods, right? There we go. 1, 2, 3, 4, 5. 5 periods of tangent, right? All right, there you go. Okay. Let's move on real quick. Cotangent. Yup. It's exactly what you're thinking. You're probably thinking, oh, that looks a lot like tangent, right? It is. It is a lot like tangent. It's exactly tangent, but it's the other one. It's the other direction. So if you remember, right, and I'm going to draw it using my space pen, tangent does this. It goes from down here and it goes upward. It goes from down here, it goes upward. It does this. It does the exact opposite from cotangent, from what you see that cotangent is doing, right? That's the only difference, okay? Well, that and the asymptotes. The asymptotes are a little different, but we'll cover that right now, okay? You guys see that the entire process is still the same, though, okay? Okay, but why? Again, why are those asymptotes there, right? We do exactly the same thing that we did with tangent, right? If you recall, cotangent, right? Cotangent is cosine of x divided by sine of x, right? Asymptotes happen, right, when the bottom, the sine of x, has to be equal to 0, okay? If you recall how sine and cosine work, right, on the unit circle, sine is the y portion, right? So then that means these values, okay, these values, 0, pi, 2 pi, 3 pi, 4 pi, okay, and they go backwards too, minus pi, minus 2 pi, dot, 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 and then on the other side, right? Okay, all of these angles have the sine component of them, the y component of them, equal to 0. And there's where our asymptotes are. Okay, so cotangent has asymptotes. They will be undefined, right, and have asymptotes whenever x is equal to any of those values up there. Okay? This is the theory behind it. This is the theory behind it, right? Thankfully, we don't remember that stuff. At least not necessary to do so, right? What we really remember, just like before, is that. Okay? We just need to figure out where the asymptotes are. Okay? Thankfully, the process is nearly identical to what we just covered for tangent, right? It's that thing that I highlighted in yellow, right? Now, just keep in mind again, right? So here's where the confusion comes. For tangent, that k value had to be odd, right? For tangent, the k value had to be odd. For cotangent, k can be any whole number. So it can be 1, it can be 2, 3, 4, 5, 6, 7. It can be 0, -1, -2, -3, -4, so on and so forth. Okay? But for tangent, it had to be odd. For tangent, it had to be 1, 3, 5, 7, 9, 11, da 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 da. Okay? Okay. But after we find out what the vertical asymptotes are, right, we can grab all of this and just throw it into a graph and we'll be good. Okay. And that's exactly what we're going to do in class. I am giving you guys some trig functions and I want you guys to graph them. Okay. I want you guys to try to graph these without using a graphing calculator, even though we have it, right? And even though I've been saying we're going to be using that graphing calculator as much as possible, even though we're going to be using Desmos as much as possible, right? I want everybody to try to do this without using a graphing calculator, okay? Just get some practice in for how to graph something like this without having that tool available, okay? Okay. Last thing I got to cover. The last two functions that that we need to cover, secant and cosecant. Okay. Secant and cosecant, they tend to be a little funky. Okay. You can graph them using the same techniques that we were doing sine and cosine with, right? And you can also do them the way that we were doing tangent and cotangent with, right? So if you take a look for both of these, let me actually put these front and center. There we go. If you take a look at both of these, they have the exact same bit of information. You guys see that? I'm highlighting it for secant there, and for cosecant, it's this. There we go. Okay? But let me point this out. You guys see these green sections that are up here and green sections that are down here. Both of those combined are secant, and both of these combined are cosecant, right? Okay. So how do we figure this out, right? If we only find just the asymptotes, how do we know that it's not this one and not this one? How do we know if our U shape is going to be facing upward or downward, right? So the easier way to do this, right? And this is the process when we need to graph these without any graphing utilities, okay? Is we graph the associated regular trigonometric function, okay? So what for secant, right? We graph this instead, a cosine bx minus c plus d. We graph this instead. Okay, that is that function right there. Hopefully you guys see it in the middle, right? And then likewise, for cosecant, we instead graph a sine of bx minus c plus d. So recall real quick, right, that secant of x is 1 over cosine, right? And then cosecant is equal to 1 over sine of x, okay? Again, right, you guys see this, right? Those are my identities. We are actually graphing the sine and the cosine versions of these graphs, and that is exactly what is happening straight down the middle. You guys see that? So the actual way that we graph these functions without using a graphing utility is we end up graphing these first. We end up graphing the good old regular sine and the good old regular cosine of these of secant and cosecant respectively, right? And based off of that, right, we figure out which one's top or bottom. So if when we graph sine or cosine between two asymptotes, if we graph it and we have the hump, we know that that U shape is going to be facing upward, like this, like what's happening right here. Okay, and likewise, if we have two asymptotes, and between those two asymptotes, we have a trough, we have a dip, right? Then we know that U shape is going to be facing downward. That's it. So if you're able to graph sine and cosine, right, it's not too far, it's not too much more work to figure out how to graph secant and cosecant. Okay? Uh, for the for the purposes of this class in particular, the 210, 210S, I'm going to concentrate a little less on this, though I do want to sort of at least cover how these things come about. Okay? And guess what? We are done. Up next is lecture questions, okay? If you have any questions on the stuff that I've covered up to today, up to now, please ask me during our quick check time or come downstairs to the tutoring center and ask me there, okay? Cool, awesome. Besides that, happy studying.